Hi, and welcome to another series with the Maths Coach. This series, we're exploring the Euclidean geometry topic at grade 11 level. I really hope and trust that at the end of you watching all these videos that I've put together, starting Euclidean geometry from its basics, from the first basic theorem up to the very last, and solving complex procedure type of problems, I hope you'll have a clear understanding that is sufficient enough to score you an A in this section of mathematics. I love this proverb. I was told it's a Chinese proverb. It says, I hear and I forget. I see and I remember. I do and I understand. I found it to be very fundamental as far as mathematics is concerned, because you'll understand that hearing what I say here, you are likely to forget. I will put some visuals so that you at least remember, but then most importantly, I want to emphasize the fact that you've got to go and practice whatever it is that I put for you as a challenge. If I ask you to try some, please do that. And make sure that you try that without looking at the memo and all that. Just put yourself into an exam type of situation and see if you can solve that problem without referring to the memo. Should there be any challenges, I implore you, I advise you, put up a comment in the comment section. I get a notification and I'll have a look and try and reply as soon as I can. I would also appreciate some feedback. If there is something that is unclear, please do put that in the comment section so that I may know how to rectify that in another video. All right, without further ado, let's kickstart our story. And we're going to kickstart our story using the first theorem that you will probably be familiar with. And for that theorem, I want you to have a look. I want to give you the visual of the theorem, and I trust that you will not forget. After that, I've got a lovely application here, or software if you like. It's called GeoGebra. And so we are dealing with circles. So I'm going to put up the circle here. And I don't mind if you have a look as to how I use this. It will be helpful for your reference as well. Now, we are dealing with a theorem that says if a line is drawn from a center such that it is perpendicular to a chord, then that line bisects the chord. And we have the reverse statement, which we call a converse, that says if a line from the center bisects the chord, then it must be perpendicular to that chord. So as you can see, I have my circle here, and I've got the line from the center, and I'm going to make a claim that this line is actually perpendicular to the chord. Do note that GeoGebra can actually verify this for us. If I were to adjust this, maybe I should, and maybe I should adjust this chord here. I should adjust this chord here, and I'm going to measure this angle. Fortunately, GeoGebra can help with that. There we go. Bravo. The angle is exactly 90 degrees. So we can see it is actually a statement that is true. We are not just making it up. So what does the theorem say? And I'd like you to know this theorem in full, not just in terms of the abbreviations to say line from center, etc., and etc., and so forth. I would like you to actually know exactly what it says in words. All right. I just want to make a disclaimer that please listen more to what I say than what I write here. I don't really have the neatest handwriting. I try, but it will be important to pay attention to what I say more so that you understand what I have written. So that's what we see. The theorem says if a line is drawn from a center and it is perpendicular to a chord, as you can see, there's a 90-degree angle, then that line bisects the chord. Whether GeoGebra knows this theorem or not, again, I can guarantee you it does actually know the theorem. And I'm going to show you that it does by measuring the two segments. So let us measure these, and so we get to see exactly if this theorem is just something we are told in the textbook, or it is a generally true thing. So as you can see, BD is 4, so we must expect CD to be 4. And indeed, that is true. So we know this. We know that this is actually true, all right? So let us write this theorem down and note it for reference. We're gonna go into an example later on. So let's refer to it as theorem 1. And what does it say? If a line is from center, so I'll write this line from center perpendicular to a chord. So this is the condition of the theorem. So in other words, this is what you have to look out for in the diagram. If you realize that there is a line from the center and it is perpendicular to a chord, then that line must bisect the chord. So a line from center perpendicular to a chord, what does it do? It bisects the chord. Every theorem that we're going to discuss will have these two components. It will have a condition, the if statement, and the conclusion, which is the then statement. So I need you to be open-minded to this. Make sure that you follow and understand what the condition is and what the conclusion is for each and every theorem. So we know here that because this line is from the center and it is perpendicular, then it will bisect the chord. And so I can conclude, once I see that this thing is drawn with a 90-degree angle, I can conclude that this thing is equal to that, all right? Now, we know that this theorem has a converse. The theorem has a converse. And what is the converse? The converse is just the reverse of the theorem. And in the converse, whatever was the conclusion becomes the condition. In essence, it becomes the if. So this thing will become the if, and then whatever was the condition in the actual theorem becomes the then part or the conclusion part. But how do we write the if? This will be the if for the converse. If a line from a center or from the center of a circle bisects a chord, bisects is the key word, bisects a chord, then that line must actually be perpendicular to the chord. Okay? And what are the key things there? In the condition, the key thing was that the line is perpendicular to the chord. So I hope you see how that has now become part of the conclusion. Similarly, what was in the conclusion, the word bisect, has now become what the if in the converse statement. So these are very important concepts to understand, and I've seen a lot of students confusing the two. I can see that the student knows the theorem, but they have written the converse, and unfortunately, I cannot mark that correct. And that's what happens in your final exams. That's what happens also with whoever is assessing you or marks your exam script. You need to say things that actually address whatever is in the diagram. So I hope you have understood this. I'm going to pause here now and go straight into solving a question and see how we will actually apply this. And so here is our first worked example in this geometry series. The statement is given there. It says O is the center of the circle. And here's one of the things that I would like to stress out. And I will show you, I'll illustrate this throughout our videos. Whenever you read a question in geometry, one of the important things that you must do is to make sure that you are able to link what you are reading with what is in the diagram, okay? So we are told O is the center. So here is the center that they're talking about. Now, what else are we given? We are given that AP is equal to PB. So look at AP. Here is AP and here is PB. And these two are equal. This sounds like the converse of the theorem that we just discussed. I hope you see that. If you've seen it, well done. Now, what can we conclude? Well, the converse says if a line from the center, that is the line OP, by the way, bisects the chord, then that line must be perpendicular. So we have every right to conclude that the angle P2 is 90 degrees because that's what the converse of the theorem says. So just reading this first sentence up to here, we have gathered some important information. Let us read the rest of the statement. We are also told OQ is perpendicular to CD, and there is our right angle. There is OQ, it is perpendicular to CD. This sounds like the exact condition of our theorem that says if a line drawn from the center is perpendicular to a chord, obviously this is chord CD, then that line must bisect the chord. In other words, we can conclude here from the theorem that CQ is actually equal to DQ. Without even knowing what the first question is, we are already putting some critical information here. Furthermore, we are then told that AB is 6. Now think with me. If AB is 6, then clearly AP will be 3 and PB will also be 3 centimeters. Similarly, if I know that CD is 8, and by the way, please do not mistake that for the circumference. When I'm talking about CD, I'm talking about that. If this is 8, then surely CQ is 4 and DQ is also 4. Now, they are mentioning a very lovely word here called the radius. And the radius is 5. So in other words, this length here is 5, but is that the only radius? No. There is another one, which is 5. And right there, I would like to give you another hint when it comes to these problems. The moment the center is mentioned, look out for your radii. Word of caution, OP is not the radius, OQ is not the radius either, because the definition of the radius is that it is a line drawn from the center to the circumference. So P ends somewhere within the circle and so does Q. So we cannot refer to those as radii, that is OQ and OP. We cannot refer to those as radii. Now, I hope you do see the right angle triangles that we have. And I can tell you, I'm already confident that whatever question they're going to ask here, we will be able to answer it in full. Well, let us see. What is the question at hand? The question at hand, we must find with reasons the length of OP and PQ. I'm sorry if you cannot see that due to my sketch. But then we must find OP and OQ. That is the question at hand. And we know we learned how to solve for X in the lower grade. So I will refer to OP, this length here that I'm supposed to find. I will refer to that as X, and maybe I will call OQ Y or another letter K, etc. Or you can still even use OP, maybe if you don't want to forget. So we are looking for this. Now, look at what we have here. Clearly, this is also a right angle, angles on straight line, or still using the converse of the theorem. So if I have this side as 3 and that side as 5, then clearly using Pythagorean triples, I know that this side here is actually going to be 4. Otherwise, you can use the theorem of Pythagoras in full and you will get that. And just like that, I have answered the question. However, I know someone is wondering, but wait, how do I write this in such a way that I will get all the marks? And that is where now I will be of help to you, because I do get to set these papers and I do get to put the marking guidelines. So I want to invite you to set up a T table. It's time to have some tea, right? Let's do that. Here's a T table, and please, you will get used to it. Don't worry. Geometry, for me, I often say to my students, geometry is tea time. So on the right-hand side, you will have your reasons. On the left-hand side, you will have your statement. And I want you to see how, and sit back and let's just enjoy the tea as it is served here. First of all, the statement that I'm going to start with is the statement that establishes that I've got a right angle triangle. So I will start by indicating that angle P1 is actually 90 degrees. Why? Because I have been told that a line from the center bisects the chord. That is what is given. O is the center. What tells me that the line bisects is the fact that AP is PB. And we know the converse of the theorem says if a line from the center bisects the chord, then it is actually perpendicular to that chord. That's my first statement. That could be 1 mark for this and another mark for that, depending on the mood of the examiner. Sometimes they will just say 1 mark for both the statement and the reason. So whether it is 1 mark or allocated 2 marks, please write both the statement and the reason. The next thing that we're going to do now that we have justified why that thing is that, we will then also declare that, well, AP must be equal to PB. In fact, we know this, it was given, there it is, there it is, there it is. So AP is equal to 3 centimeters, since AP is equal to PB and we have AB is equal to 6 centimeters. And I don't think at this stage we really need to justify this. If you feel insecure, like, no, my teacher is too strict or so, it's fine. You can write that it is given that AB is 6 centimeters. All right. We're going to take note of that. And obviously AO is also 5. We don't need to actually write those, but I'm going to write this because I've been given that thing bisects that. And so therefore we will go and say OP is equal to 4 centimeters. And the nice thing about paper 2, by the way, is that you are given an answer booklet. And so because you are given an answer booklet, you will be able to indicate this on your sketch. So do not stress much. So OP is 4 centimeters. Why? Pythag. And here I'll say Pythag triples, because really I know that if I have 2 sides as 3 and 5, the other side must be 4 in a right angle triangle. Sometimes examiners are, find it easy and appreciative if you indicate which triangle you're working in. So I'm going to indicate this triangle APO to make it easy for the marker to see what I'm talking about. All right, let us wrap this up. Obviously, I have to find OQ, and it is obvious that OQ will be found using the same argument. Let us have the T table on this side here. So how do we calculate, or do we find OQ justifiably so? I hope you can see again Pythag triples. OQ should actually be 3. And by the way, what makes me to find OQ? Well, it is the fact that I've been required to calculate PQ. So I need to know what OQ is so that I know the entire length of PQ. So it's quite obvious, since I know that this is perpendicular, I will then conclude here that CQ is equal to DQ. Why? Because in this triangle, I am told, or I know from that statement, that line from center was drawn such that it is perpendicular to a chord. And so it must bisect the chord. Therefore, CQ is actually 4 centimeters. The radius is already given. Therefore, OQ is 3 centimeters. All right. Y again, Pythag, you may say in triangle OCQ or OQC, your chord, but doesn't really matter and doesn't make much of a difference at this stage. So finally, we can say, therefore, PQ is equal to PO or OP plus OQ And this is what? 4 plus 3, which is 7 centimeters. Lo and behold, we have answered the question in full. The follow-up question that was asked was, why is the line AB parallel to CD? Well, this is where now your grade 8 and grade 9, as well as grade 10 knowledge comes into play. You need to note that co-interior angles in this diagram add up to 180 degrees. And I'm going to put this one here in pink. I need you to note that this angle and that angle, both 90. So your reason would be co-interior angles are supplementary or add up to 180 degrees. Go ahead and try similar problems like this. Of course, at the end, I will actually put up some exercises in one separate video. You will see that. For now, I just want to spend time explaining these theorems. So I want you to go ahead in your textbook, grade 11 textbook, or just Google a worksheet on a theorem like this. Try and see if you can solve basic problems on this. The next question that I'm going to solve, it will be on this theorem as well, but it will be an abstract question. So tune in, subscribe, so that you get notifications when that question comes. Thank you for watching this video.